Today, I would like to introduce you about the topic of Markov chain. Briefly, a Markov chain is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state attained in previous event. At each step of Markov chain, the system can change from one state to another, or keep the current state according to the probability distribution. We have transition matrix to describe the probability. The change of a state is called transition, and the probability related to different state change is called transition probability. Random walk and the Brown motion is one example of Markov chain. The state of each step in random walk is a point in the graph. Each step can move to any adjacent point. The probability of moving to each point is the same here, no matter what the previous walk path is. Let me talk about the definition. The discrete time Markov chain is a sequence of random variables, with the Markov property named that the probability of moving to the next state depends only on the present state and not on previous state. If both conditions, as the graph shows, probabilities are well defined, that is, if on the other hand, the continuous time Markov chain, defined by a finite or countable state space S, a transition rent matrix Q with dimensions equal to that of the state space and the initial probability distribution defined on the state space. For I is not equal to j, the elements Qij are not negative, and describe the range of process transition from state I to state j. The element Qij are chosen such that each row of the transition range matrix sum to 0. Let me talk about the Markov modeling. At first, we choose the naive model, iteratively multiply the transition matrix and convergence to a stationary vector. As the graph shows, we could run the sample. As the graph shows, the vector of the current state are convergence to constant. And
next is the stationary distribution. One easy example is that today is rainy day and tomorrow is rainy, has a probability 0.7. If today is sunny day, then tomorrow is rainy and the probability of 0.5. From that, we can know the probability of Monday rains and Wednesday also rains is 0.64. We have the transition matrix Q and Q square. Q square 1 is probability from Monday rainy to Wednesday rainy. To extend that, we want to know what's the probability that one day is sunny day. That means we need to know that what is QK. And Q is a closed loop, so we know that the Markov chain has the stationary distribution pi, that pi is equal to pi q. We got pi is 0.625 and 0.375. So for a day, it is 0.625 to be rainy day and 0.375 to be sunny day. From the example, we know the Markov chain has a stationary distribution. A stationary distribution is a Markov chain is a probability distribution that remains unchanged in the Markov chain as time processed. In linear algebra, may note that the equation pi is equal to pi q looks very similar to the column vector equation. A times vector v and pi times vector v for eigenvalues and eigenvectors with lambda is equal to 1. In fact, by transposing the matrices, pi times q transpose is equal to pi transpose, and from that we know q transpose times pi transpose is equal to pi transpose. In other words, the transpose transition matrix q transposed has eigenvector with eigenvalue 1 and 1 that are stationary distribution expressed as column vectors. Therefore, if the eigenvector of Q transpose are known, then so we also know the stationary distribution of the markov chain with the transition matrix Q. In short, the stationary distribution is a left eigenvector. And we use Julia. We have the code like this. And another application is PageRank.